Hello everyone, this is lecture 63 of Principles of Electric Circuits. After introducing the concept of resonance in the last lecture, we will discuss RLC resonance in detail in this lecture. Firstly, we focus on the RLC series circuits. We need to draw its phasor graph. First, we mark all branch variables. We define the current as the reference phasor. UR and I are in phase. UL leads I 90 degrees. UC lags I 90 degrees. So the voltage and the current are in phase. In the last lecture, we've derived that the resonant condition of the one-port network is this. And the result is this. We've also derived that the input impedance of the port in resonance is a resistance. Now we discuss the voltage of the energy storage elements in resonance in detail. Firstly, we calculate the current. Then we focus on the voltage of the energy storage elements in resonance respectively. The first is the inductor's voltage. By substituting resonant angular frequency of this expression, we get this. Similarly, we can calculate the capacitor's voltage in resonance. By substituting resonant angular frequency of this expression, we get this. These are the voltages of the energy storage elements in resonance. By substituting resonant angular frequency for this expression, we can find that the voltage of the energy storage elements in the resonance are the same. It's the same as the conclusion we gotten from the phasor graph. If this is the parasitic resistor of the inductor, its resistance will be very small. In this condition, the energy storage elements will get high voltages. In other words, the energy storage elements in series RLC resonance may have higher voltages than the port. So RLC series resonance is also called the voltage resonance. Next, we'll see experiment of the RLC series resonance. This is a serial RLC circuit. The input is a sinusoidal signal on board. The output is the voltage of the resistor, which is proportional to the current. We can change the frequency of the input signal to observe the resonance of the circuit. Channel 1 of the virtual oscilloscope is connected to the input signal, and channel 2 is connected to the output. Let's look at the waveform on the oscilloscope. The yellow waveform is input voltage. The green one is output voltage. We can see the input and output voltages are in phase, which means the circuit is in resonant condition. Now we adjust the frequency of the source higher, and we can see the input and output voltage aren't in phase anymore, and the amplitude of the output voltage is smaller than that in resonant condition, which means in resonance the output voltage reaches its maximum value. Also, the current in the circuit reaches its maximum value. Obviously, we can observe the similar phenomenon by adjusting the frequency of the source lower.